Martingales. Here's what a martingale is. A martingale is a process that is a random function of t, which is adapted to a certain filtration f as a function of t. That's to say, just to remind you what that means, xt is measurable with respect to ft. So among those things that you're supposed to know at time t is the value of xt. It doesn't have to be any particular kind of process really, it doesn't have to be an Ito diffusion, it doesn't even really have to be a Cadlag process, although all the ones that we consider will be. The important property for being a martingale is this: the expectation of what it's going to be at a later time given what it was at an earlier time. So this is for s being the earlier time and t being the later time. So we're given everything up to the earlier time s, and we want to know what's the expectation of what it's going to be by the time we get to time t is just xs. So the expectation of what it's going to be in the future is always the same as what it is now. Or a very slightly different way to write that, sometimes we put the xs over here and write it like that, because the conditional expectation of xs given fs is itself. You're supposed to already know the value of xs by time s. So when we write it in this form, you can say in words, for a martingale, the expectation is always for no change in the future. The upcoming increment between times s and t has a conditional expectation of 0, conditional on having seen everything up to this point. So that's a martingale. It's a very important kind of process that has quite a lot to do with stochastic calculus, as we'll see. This is what it is when t is a continuous parameter, so everything's a function of continuous time t. There's also a version in discrete time. So for that it would be xn. So now we've got not a random function but a random sequence, or a sequence of random variables, same thing, indexed by n, with n going from 0 to infinity. And likewise the filtration. And then again that means xn should be measurable with respect to fn. And the condition would be the same. The conditional expectation of what it's going to be at a later time, given what it was at an earlier time, is what it already is at that earlier time. Or, in the discrete case, there's actually a slightly easier way to write that. Instead of having m and n, we can just have n and n plus 1. So this is the statement of the martingale property when we're looking only one step ahead, one time step, just from n to n plus 1. So the conditional expectation of what it's going to be one step in the future is what it already is right now. Obviously this is a special case of the general statement, but it's actually equivalent. You can actually see that if you have the property when you're looking only one step ahead, you also have this when you're looking any number of steps ahead. Let's just see why that is. It's just a one-line thing to check. because if we were looking k steps ahead, so this is xn plus k, well, one way to get that is to say, remembering the smaller sigma field wins rule for conditional expectations, write it like this. First we'll condition on Fn plus 1, which is a bigger sigma field than Fn, but then we'll condition again on Fn. Since Fn is the smaller sigma field, ultimately the answer we get is the same as if we were just conditioning on that. And now, what's this thing we have inside? Well, now this is looking only k minus 1 steps ahead, so if we're going for an inductive proof here, we can say, suppose we've already got it for only k minus 1 steps, then that would say that this is just like so, and again we're assuming we've already got it for 1 step as well, so xn. So proof by induction, if we already had this, what we're trying to establish for 1 step and for k minus 1 steps, then we have it for going k steps ahead as well. So that's a discrete time martingale. Actually, the discrete time case can be thought of as a special case of the continuous time one. If you like, this is not terribly important, but if you want to consider the two cases together, you could say we've got a discrete time one, that is, we've got a random sequence that is defined at these times only, 1, 2, 3, 4, like this, so it's only defined at integer times. This is x0, this is x1, this is x2, right? A random sequence. Well, if you want to think of that as a function of continuous time, all you've got to do is draw the straight lines in between. Just do linear interpolation, and then you've got a random continuous function of continuous time. And if the original sequence, the original discrete sequence you started with was a martingale, then this random function constructed in this way is a martingale according to the continuous time definition. So that's just a way of fitting both definitions together so you can kind of consider the discrete time to be a special case of the continuous time. What are some examples of martingales? Well, there's quite a few actually. Let's start with one of our favourites, the simple random walk. Remember what this is? We have some independent, identically distributed random variables, z1, z2, and so on. They're the steps. They are plus and minus 1, with probability of half each. And where the walk has got to by time n is just the sum of the steps up to time n. That's the simple random walk. Why is that a martingale? It's a discrete time one, obviously. Well, the thing we need to check is this. So let's look at the conditional expectation of what it's going to be 1 step ahead, given that we've only seen up to step n. So let's see 1 step ahead. Well, the best way to write this probably is it's xn plus 1 more step. So xn plus the n plus 1th step. Xn is supposed to be measurable with respect to Fn, so its conditional expectation given Fn is itself. And I haven't actually said what Fn is, but let's just put that in for clarity. Fn is all the information you have up to step n, so you know the first n steps. So the sigma field generated by those random variables. All right, and now what's Zn plus 1? Well, it's supposed to be independent of Z1 to Zn, which means it's independent of Fn. So actually the conditional expectation is the same as the unconditional expectation by the independence. But the expectation of Zn plus 1 is 0. So that's just xn. So conditional expectation of what it will be after one more step is what it is now, which is the property for a martingale. So the simple random walk is a martingale. For another example, Brownian motion is an example of a martingale in continuous time. So here our process Wt is a Brownian motion. And our filtration, the Ft, is given by Ft is just all the information you have up to time t, so it's the sigma field generated by all the random variables Ws for S having every value up to t. So again, Ft is all the information that you have if you've seen the process up to time t. Alright, let's just check this martingale property for Brownian motion. What's the expectation of Wt given Fs when S is an earlier time than t? So we'll do like we did for the simple random walk. We'll break it up like this. And now we've got Ws. Well, Ws is supposed to be known at time s, so its conditional expectation will be itself. Now the next increment of Brownian motion from time s to time t, that is Wt minus Ws, that's supposed to be normally distributed with mean 0 and independent of the previous increments, all increments over previous intervals that don't overlap this one. So in particular it's independent of Fs. So the conditional expectation is the same as the unconditional one. Knowing Fs tells you nothing about what this is going to be. And what is this conditional expectation? Well, this increment has a normal distribution with mean 0, so the expectation is 0. So, conditional expectation of what Wt is going to be when you only know things up to time s is what the process is right now, Ws. That's the martingale property. Third example, the doubling strategy, or doubling down. This is something that has a long history in gambling. Martingales actually have quite a close connection to gambling, as will hopefully become apparent as we go along. So in this story, we're just going to bet on coin flips. You can apply this to any gambling game, but let's just keep it to betting on a sequence of coin flips. So every time you flip the coin, you make a bet on whether it's going to land head or tails. And if you got it right, if you win some amount of money, whatever the size of your bet was. And if you get it wrong, then you lose that amount. So it's a fair game. You're as likely to win as lose. It's a fair coin. And your strategy is going to be that you'll start by betting $1, and then if you win the first flip, that's great, you've won $1. And if you lose, you will double the bet next time. So your next bet on the next coin flip will be $2. And then if you win that, well, then you lost 1 on the first flip, but you've won 2 on the second flip, so you're up by 1, which is good. The only bad outcome is if you lose 2 flips in a row and then you're down 3, but that's okay because your next bet is going to be $4. You double down again. And then if you win, you make good your $3 lost and you still end up by $1. If you lose the third flip too, then, well, now you're down 7, but that's all right because your next bet is going to be 8. So you'll have enough to make up all those losses, provided you win it. If you lose it again, of course, well, now you're down 15, but the next bet will be 16, and so on. So, not without wanting to offer any opinions on whether this is a good strategy for gambling or not, you can kind of see what's going on here. This, by the way, is sometimes called the martingale. In old books on gambling and probability, if you come across a reference to the martingale without any further explanation, often this is what it means, just doubling down in gambling. So let's write this down mathematically, and so we can see where the martingale is. So let's say we've got Z1, Z2, random variables. These will be IID. They're a favourite kind, plus or minus 1 with probability a half each. These are going to be the outcomes of the coin flips. So plus 1 if you win, and minus 1 if you lose. And xn will be amount of money we have after n flips. So after you've made n bets, this is how much money you have. And the rule for that is that how much money you have after n plus 1 is how much money you had before, plus whatever you won or lost from the n plus first flip. And how much is that? Well, basically it's this z, plus or minus 1, but it gets multiplied by the size of the bet you made, which we'll call bn. That's the size of the bet. And bn is determined by this doubling rule. You can try to write that down mathematically, but I'll just content myself with saying bn doubles after every loss. What are the sigma fields here? Fn is what you know after n flips. After n flips, you've seen the results of the first n flips, so that's just sigma of z1 to zn. And the key thing to observe about this process, the thing that makes it all work, is to note that bn, the size of the bet that you're going to make on coin flip number n plus 1, must be measurable with respect to Fn. So actually this mathematical formalism would cover not only doubling down, but any kind of gambling strategy. Any sensible strategy, no matter what it is, has this property that the size of the amount that you're going to bet on the n plus first flip has to be some kind of a function of what the first n flips were. So it must be measurable with respect to Fn. That means that we can look at this to check the martingale property. And what is it? It's how much money you had before. Xn plus 1 is how much money you had before, plus how much you're going to win or lose on that bet. Xn is known at time n, so that its conditional expectation is itself. And now Bn is measurable with respect to Fn, which means in this conditional expectation it can be treated as a constant. It can be pulled out. Bn is supposed to be known at time n, so if we're conditioning on Fn, we can treat it as a constant. And that leaves us with this, which, as we've seen before when we're doing the simple random walk, this conditional expectation of what the next flip is going to be, plus or minus 1, is the same as the unconditional expectation by independence, and the unconditional expectation of Zn plus 1 is 0. So we're left with just Xn. Conditional expectation of how much money we're going to have after making one more bet is the same amount of money we have now. The actual distribution of the amount of money we're going to have after one more time step may be quite wild. It depends on the size of the bet. It could be that if you make a big bet, you end up with a very different amount of money. But the expected amount is the same as what you've got now. And that somehow relies on the fact that we're playing a fair game here. The coin is fair. So there isn't really going to be a way to consistently make money out of a gambling strategy that depends only on looking at what's happened in the past. Okay, martingales have one really important property that is really the key to why they're so useful, and that is that they have constant mean. That is, if you've got a martingale xt, then the mean of xt, expectation of xt, is the same value for all t. So the actual distribution of xt could be very different for different values of t, but it's always with the same mean. Why is that? Well, it just comes directly from the martingale property, which remember is this. If you have 2 times s and t, with s being the earlier one, the conditional expectation of what xt is going to be at time t, given only what we know at the earlier time s, is just whatever it was at the time s. And all you have to do to get from that to constant mean is just take expectation on both sides. And then here on the left we've got the expectation of a conditional expectation, and the expectation of a conditional expectation is just the expectation. It's the smaller sigma field wind rule again. So this is just the expectation of xt. So this is for any s and t, any 2 times s and t. The mean of xt must be the same as the mean of xs. The way we most often use that is by looking at time 0. So the expectation of it at any time t must be the same as it was right back at the beginning at time 0, and most of the martingales that actually come up often are very simple at time 0. Typically they start out having a constant non-random value at time 0, so whatever that number is, that number is also going to be the mean of xt for every other value of t. So for example, with the doubling strategy, we have x0 is the amount of money you had before you started gambling, so that's whatever it was, some fixed non-random amount of money. Then you can conclude that the expectation of how much money you're going to have at any later time t is also x0. So on average, you can't win money by using clever strategies at gambling. On average, that is. Of course, you can sometimes win money and you can sometimes lose it, but on average you will always have exactly the amount of money you started with.